Oh, hi. Didn't see you there. My name is Boss, and we're going to paint some happy trees. But first, let's talk about relative velocity. Whoa there. Relative velocity is an object's velocity relative to the position of an observer. For example, if a person was going 45 meters per second and an African swallow was also going 45 meters per second, it would look like the bird is unmoving to the observer. So we can just draw this out right here. Here's a person, like a handy dandy, 45 meters per second. And there's this little African swallow. Yep, beautiful. Look at that, also at 45 meters per second. Now if the observer looked at the bird, it would look like the bird's unmoving because they're both going the same velocity. Another example of relative velocity can be shown in this Mythbusters example. In this example, a truck is going at a specific velocity and a cannonball is being launched from the back with an initial velocity the same as the truck. From the person driving the truck, it looks as if the cannonball is being launched away from the truck, while from someone observing the truck, it looks as if the cannonball is just falling straight down. Another way to represent relative velocity by using this kinematics equation. Vf equals vi plus at. Final velocity equals initial velocity plus acceleration times time. Represents this situation because the ball's initial velocity is the same as the truck's and is launched from a cannon behind the truck. The ball will have a negative acceleration because it is moving in the opposite direction for a positive time t. The ball appears to only fall down because the equation equals a 0 horizontal velocity.
Oh hey, my name is Rob Boss, and did you want to learn physics? Well, guess what? You came to the right place. Alright, my name is Rob Boss, and I'm Boss's brother. I'm going to tell you about projectile motion. Ladies, you thought you were going to paint happy trees with Corporal Robert Boss? You were incorrect. We're learning about projectile motion. Alright, you thought otherwise? You thought otherwise? That was cute. It's cute of you, private. But you're in my military right now, and I want you to focus up on this rocket that we're launching from home base, all right? That's enemy base. The rocket is going to undergo projectile motion before it hits the ground on enemy base. It will have a vertical component of motion and a horizontal component of motion. And the only acceleration that rocket will experience is the downward acceleration, because we're assuming that rocket has no acceleration from the propulsion system, all right? Because we're cool like that in the military. Private. Let's cut to a clip of this actually happening.
Oh shoot.
Private. If you were paying attention in that video clip of the rocket crushing the enemy base, you'll notice that we can graph that motion in 6 specific graphs, all right? 3 for vertical and 3 for horizontal. Let's start with vertical acceleration. That is going to be negative, as you can tell by the arrow, because that is gravity crushing your hopes and dreams. This is velocity, and it starts positive, but it heads towards 0, and then it speeds up in the negative, because that follows the distance of the rocket as it comes up and then goes back down again through the archway. You think you were done? Wrong! We have 3 more graphs to do. Private! This is going to save your life one day. In the horizontal portion, we don't have acceleration. Alright? You thought we did. That's funny. This is velocity, alright? It's constant. It's constant velocity. My name is Robert Boss. I'm your corporal, and I say it's constant because it is projectile motion. The distance, it's going to land like that. It's going to travel a horizontal distance and then reach 0. That's how graphs work. Corporal Robert Boss. Me. All right, private. private. If you can't tell, it's nighttime. That's because you were too dumb to understand it quickly enough. Not because of multiple takes. I'm corporate Robert Boss. I'm perfect. I don't need multiple takes. Cut. Just kidding. That wasn't a multiple take. I'm perfect. Let's learn about kinematics. That is your final distance. That is your initial horizontal distance. That is your horizontal velocity. That is the time it takes it'll travel through the air. That is half, because that is important. That is the acceleration due to gravity, soul-crushing, beautiful gravity, just like Mama used to make. That is the time it takes for the rocket to travel in that horizontal distance. But guess what? That one, remember what I said about gravity? I lied. Private. I'll do that sometimes to break your spirit. That one, you don't use it in horizontal velocity. Horizontal distance. This is kinematics. Let's look at vertical. This is the final vertical. This is the initial vertical distance. That is the vertical velocity. That is the time it takes. That is half. That is the acceleration due to gravity. That is the time it takes. Just like that T, except that one's squared. And if you want to find half, excuse me, private, if you want to find the maximum height, you plug in half the time. That's kinematics.
My name is Bill Robs. I'm tired.
Okay, so we're gonna paint some happy trees. But first, we need to do some physics. Anyways, I'm gonna talk about one-dimensional motion. And my interest is a perfect example of that, where I am sliding across the floor. There's only an initial velocity and an acceleration due to friction that causes me to accelerate in the opposite direction of my velocity until my final velocity is equal to 0. So, in my example of me sliding across the floor, we can use this equation where Vx squared is equal to Vx initial squared plus 2a times the change in distance. So, in that example, we have my final velocity, which will be equal to 0, and then my initial velocity, which is a set velocity. You square that, and then you also add it to 2 times the acceleration times the change in distance that I traveled while I was sliding. So, we can use a motion map to visualize me sliding across the floor. This is the distance that I traveled, and we're going to assume that I slid across the floor for a total of 5 seconds. At t equals 1 second, we have initial velocity, where I travel from here to here where t equals 2. At this point, the acceleration has caused my velocity to change and become slower. So we have t equals 3 at a shorter distance from here to here than here to here. So then, as time continues to move on, my velocity decreases until it comes to a complete stop at t equals 5 seconds, at which I will have traveled the distance that I slide across the floor.
Hello, I'm Bob Ross, and I'd like to welcome you. First of all, let me take just a moment to thank you for allowing me back into your homes. If this is your first time with us, let me extend a personal invitation for you to drag out your oil paints and paint along with us each week. Let's go over to the canvas here and let's get started. I believe